Welcome back to the deep dive. Our mission, as always, is to take some really complex source material and basically give you the fastest route to getting fluent. Today, we're tackling maybe the biggest shift in modern AI architecture, that whole journey from, simple sequential memory up to the attention mechanisms we see everywhere now. We're digging into sequence modeling. And the core thing here is that for some, data think language, time series, even DNA order is everything. It completely changes the meaning. Like the dog chased the cat versus the cat chased the dog. It's the same words, but a totally different story, right? And for years, getting AI to grasp that kind of order and memory, well, that was the big hurdle.
Exactly. And our goal today, for you listening, is really to map out those key breakthroughs in architecture. We want to trace how we got from, let's say, the first attempts at internal memory all the way to just getting rid of sequential processing altogether. That's what finally let AI master these things called long-range dependencies.
Long-range dependencies, right?
Yeah, and they're pretty much what they sound like. It's about connecting bits of information that might be far apart in the sequence, but are, crucial for understanding the whole picture. This was the real killer for early models. Say you have a document that starts, I was born near Bordeaux, France. Then maybe paragraphs later it says, I finally became fluent in French. The model has to link France way back at the start with French much later on. Seems obvious to us. But for early AI, that was tough.
Okay, so how did the first models try to handle that? Like the really early ones?
Well, the first shot was basically autoregressive models. The idea was simple. Predict the next thing based on, say, the last few things you saw. A fixed window of history.
A fixed window. Okay, I see the problem already.
Right. It's what we'd call architectural blindness. The model's view of the world, its context, was literally just that fixed window size. If the word France fell just outside that window, poof, invisible to the model. It was totally static. It couldn't adapt. And that limitation, that rigidity, really forced the field to think about models that could maintain some kind of ongoing internal state.
Which leads us to the RNN, the Recurrent Neural Network. That was sort of the first big workhorse for sequences, wasn't it?
It was. And the key wasn't really about speed initially. It was this idea of a recurrent connection, basically a loop. Information from one step could feed back into the next step.
Ah, a loop. So information could kind of persist.
Exactly. You use what's called a hidden state. You can think of it like a scratch pad or a running summary. At each step, the RNN looks at the new input, considers its old scratch pad summary, and computes a new updated summary to pass forward.
Okay, a constantly updated memory.
Right. And the really clever part, the efficient part, was parameter sharing. It used the exact same set of rules, the same mathematical operations, the same weights, at every single time step. That's what allowed it to handle sequences that weren't just a fixed length, but could be theoretically any length.
Okay, same rules repeated over and over. But how do you train something like that if it's looping back on itself?
Yeah, that's where it gets interesting. You use a technique called backpropagation through time, or BPTT. Conceptually, you kind of unroll that loop. Imagine the sequence has 100 words. You unroll the RNN into a super deep network, 100 layers deep, one for each word.
Wait, hold on. If you unroll it, it's just a really deep feed-forward network, basically. Why does the loop, the recurrence itself, cause this infamous vanishing gradient problem we hear about? Why is that the culprit?
That's the million-dollar question. It's because you're reusing those shared weights, that same matrix multiplication, over and over and over again at each step. When you do backpropagation, the error signal has to travel backwards through time, right, through all those unrolled layers. And at each step back, it gets multiplied by that shared weight matrix again. Now, if the values in that matrix are, generally speaking, small, less than 1 multiplying by them repeatedly makes the error signal shrink exponentially fast. It just dwindles away.
Ah, okay. So the gradient, the signal telling the early parts of the network how to adjust, it just vanishes before it gets there.
Precisely. It becomes effectively zero. So the model literally cannot learn connections between things that are far apart in the sequence. Its effective memory becomes incredibly short.
So it could maybe remember the last few words, but connecting the subject at the start of a long sentence to its verb way at the end, forget it.
Exactly that. That's the vanishing gradient problem. And it was a massive roadblock. Now, the opposite problem, exploding gradients where the signal gets too big, that's actually easier to handle. You can just clip the gradients, sort of cap them.
Okay.
But vanishing gradients, that needed a more fundamental architectural fix.
Which brings us finally to the LSTM, the long short-term memory network, right? Back in '97, which feels like ancient history in AI terms.
It really does. And LSTMs were designed specifically to combat that vanishing gradient issue. They essentially gave the network a mechanism to explicitly control what to remember and what to forget over long periods.
How did they do that? What was the magic?
The core idea was introducing a separate information channel, the cell state. Think of it like an information conveyor belt, running straight through the entire chain of processing steps.
Okay, a conveyor belt.
Yeah, and crucially, this belt is managed by special mechanisms called gates. These gates are like little mini neural networks themselves. They look at the current input and the previous hidden state, and they output a value between 0 and 1.
0 means block, 1 means let it through.
Exactly. Like little traffic controllers for the information highway. They dynamically decide what old information to throw off the conveyor belt, what new information to add, and what part of the belt's content should be output as the main hidden state for that time step.
So you mentioned 3 gates managing this.
That's right. You typically have the forget gate decides what to get rid of from the old cell state. Then the input gate decides what new stuff is important enough to add to the cell state. And finally, the output gate determines what part of the updated cell state should be revealed as the hidden state, the thing the network uses for predictions or passes to the next step.
And why did this structure solve the vanishing gradient problem? What was the key difference?
The key is how the cell state is updated. It's mostly additive. Information is added to or removed from the conveyor belt via these gates, but it doesn't have to pass through repeated multiplications in the same way the hidden state updates did in simple RNNs. This additive process creates, effectively, an uninterrupted gradient highway. The error signal can flow backwards through time along this cell state conveyor belt without shrinking exponentially. It allows the model to learn dependencies over hundreds, even thousands of time steps.
So the memory is protected, basically. It can actually remember the start of the document.
Exactly. Problem solved. Well, mostly.
Mostly.
Well, then came the GRU, the Gated Recurrent Unit, a few years later, around 2014. It was sort of a streamlined version of the LSTM.
Simpler.
Yeah, a bit simpler. It combined the cell state and hidden state into one, and it only used 2 gates instead of 3. A reset gate and an update gate. Fewer parameters, generally faster to train, often perform just as well as LSTMs on many tasks, so it became quite popular too.
Okay, so with LSTMs and GRUs, we now have models that can actually handle long sequences. This must have opened up new possibilities, like machine translation.
Absolutely. That led directly to the sequence-to-sequence, or C2SEC, framework. This was huge for tasks where the input length and output length might be different, like translation.
And that's the encoder-decoder thing.
Right. You have an encoder network, usually an LSTM or GRU, that reads the entire input sequence, say a sentence in German. Its job is to process this whole thing and compress all its meaning down into a single fixed-length vector.
A single vector representing the whole sentence meaning, often called the thought vector.
That's the one. Then you have a decoder network, another LSTM or GRU, which takes only that fixed thought vector as its starting point. And from that vector, it has to generate the output sequence, say the English translation, one word at a time, auto-regressively.
Okay, hold on. That thought vector sounds incredibly important. But if it's fixed length, didn't that create its own problem? I mean, how can one fixed size vector perfectly capture the meaning of a short sentence and a really long, complex paragraph? Couldn't you just make the vector bigger?
That's exactly the problem they hit. It wasn't just about size, though making it bigger helped a bit. It was about information density and, crucially, lossy compression. Imagine trying to summarize, I don't know, the entire plot of War and Peace into a single tweet. No matter how clever you are, you're going to lose a ton of information.
Right.
Forcing the encoder to cram everything from an input of any length into one static vector created a massive bottleneck. The longer the input sequence, the more information got squashed and lost. Performance really tanked on long sentences.
Okay, so that bottleneck needed fixing, and that fix was attention.
That fix was the attention mechanism, introduced around 2014-2015. And it wasn't just a tweak, it was a conceptual revolution. It basically said to the decoder, you don't have to rely only on that single static summary vector anymore.
So what did it do instead?
It allowed the decoder, at every single step of generating the output, to dynamically look back at all the hidden states the encoder produced for the input sequence. Not just the final summary vector, but the state representing each input word.
Ah, so it could focus on relevant parts of the input as it was generating the output.
Precisely. The analogy often used is a human translator. When you translate, you don't read the whole source sentence, summarize it in your head, and then write the whole target sentence.
No, you kind of look back and forth, right? Focusing on the words you need for the part you're currently writing.
Exactly. Attention lets the decoder do that. For For each word it's about to generate, it calculates which parts of the input sequence are most relevant right now. It then computes a weighted average of the encoder states, giving more weight to the relevant ones, creating a new dynamic context vector specifically tailored for that decoding step.
Okay, dynamic context. That makes sense. And this is where that QKV stuff comes in. Query, key, value.
Yep, that's the fundamental abstraction. Think of the decoder's current state as the query it's asking. What information is relevant to the word I need to generate next? The encoder's hidden states act as the keys. The decoder compares its query to all the keys to find matches, to see which input states are relevant.
And the values.
The values are also the encoder's hidden states, basically representing the actual content. Once the decoder figures out which keys match its query, using dot products usually, it uses those attention scores to create a weighted sum of the corresponding values. That weighted sum is the dynamic context vector for that step.
Got it. Query asks, keys answer, values provide the substance based on the answer.
You've got it. And that foundation, that idea of dynamically querying context, led directly to the next massive leap.
The 2017 paper, Attention is All You Need.
The one and only. The transformer architecture. And the most radical thing they did, they threw out recurrence entirely. No more RNNs, no more LSTMs, no more sequential processing loops at all.
Just attention. That seems bold. Why was getting rid of recurrence such a big deal?
Parallelization. RNNs and LSTMs have to process sequences step by step, one token after another. To understand the relationship between the first word and the last word in a long sequence, the signal has to travel sequentially through all the intermediate steps. That's inherently slow and can't be easily parallelized on modern hardware like GPUs.
Okay, so it's like a bottleneck in computation time.
A huge one. The transformer, using attention, changed the game. The path length, the connection between any two tokens in the sequence, became effectively constant order 1. Every token could theoretically interact directly with every other token simultaneously through the attention mechanism.
So you could process all the words kind of at once?
In principle, yes, especially within layers. This unlocked massive parallelization. You could throw enormous amounts of data and compute at these models in a way that was just impossible with RNNs. That's the real enabler for the scale of models like GPT-3, GPT-4, and everything since.
And the engine driving this is self-attention.
Self-attention, exactly. Instead of attention between an encoder and a decoder, which transformers can also do, self-attention happens within a single sequence. Each token looks at all the other tokens in its own sequence to compute a better, more context-aware representation of itself.
How does it know what's important? Is it still query, key, value?
Yep, same QKV mechanism, just applied differently. Each token generates its own query, key, and value vector. Then, each token's query is compared against every other token's key in the sequence to calculate attention scores. Those scores then determine how much influence each token's value has on the final updated representation for the original token.
Okay, so everything talks to everything else. And they use that specific scale dot product attention. Why scaled?
Ah, the scaling factor. That was a neat trick. When you compute the dot products between the query and key vectors, especially if the vectors are high-dimensional, the results can become very large. If you feed very large numbers into the softmax function, which turns scores into probabilities, the gradients can become vanishingly small, making learning difficult again. So they scale the dot products down by dividing by the square root of the dimension of the key vectors. It just helps stabilize the training.
Clever. But wait, if you get rid of recurrence, the sequential processing, how does the model know the order of the words? If everything just attends to everything else, doesn't dog bites man look the same as man bites dog after attention?
Excellent point. Pure self-attention is indeed permutation invariant. If you shuffle the input words, you just get shuffled output representations. The meaning derived solely from order is lost.
So how did they fix that?
They had to add the order information back in explicitly. They used positional encoding. Before the input words even enter the first transformer layer, a vector representing the position of each word, like word 1, word 2, word 3, is added to its word embedding. They often use sine and cosine functions of different frequencies to create these positional vectors. It's like giving each word a unique positional signature that the model can learn to interpret.
Okay, so position gets injected right at the start. What about making these models really deep, like BERT or GPT with dozens of layers? How do they make that work?
Two key things there, besides the core self-attention. One is multi-head attention. Instead of just calculating attention once, you do it multiple times in parallel with different learned transformations for the QKV vectors.
Like having multiple viewpoints.
Exactly. Different heads can learn to focus on different kinds of relationships simultaneously. Maybe one head focuses on syntactic dependencies, another on semantic similarity, another tracks negation. Whatever emerges is useful. It gives the model more representational power.
And the other thing,
Residual connections and layer normalization. These are standard techniques in deep learning now, but crucial for transformers. Residual connections add the input of a layer to its output, creating a shortcut that helps gradients flow better through very deep networks. Layer normalization helps stabilize the activations within each layer. Together, they allow training these incredibly deep stacks of attention layers.
right, okay. That brings us pretty much up to the modern era. So we have this powerful transformer architecture. How did it lead to the different types of models we see now, like BERT versus GPT?
It comes down to the modern paradigm of pre-training and fine-tuning. You first train a massive model on a huge amount of unlabeled text data using a self-supervised task, a task where the labels are derived from the input data itself.
Like predicting missing words.
Exactly. Then, once you have this generally knowledgeable pre-trained model, you fine-tune it on a smaller, specific labeled dataset for the actual task you care about, like sentiment analysis or question answering.
And the way they pre-train determines the model's basic flavor.
Precisely. This has led to roughly 3 main families of transformer architectures, defined by their structure and pre-training objective.
Okay, let's break them down. Family number 1.
First up, encoder-only models. The most famous is BERT. These use just the transformer's encoder stack. Because they don't need to generate text autoregressively, they can look at the entire input sequence at once. They're deeply bidirectional.
Seeing both left and right context for every word?
Right. Their main pre-training task is usually masked language modeling, MLM, basically, fill in the blank. You mask out some percentage of words in the input and train the model to predict them based on the surrounding context. Because they're so good at understanding context, they excel at natural language, understanding NLU tasks, things like classification, entity recognition, question answering.
Okay, encoder only for understanding. What's next?
Second, the decoder-only family. Think GPT. These use just the transformer's decoder stack. Crucially, they use masked self-attention, meaning each token can only attend to previous tokens and itself. This enforces the autoregressive left-to-right behavior needed for generation.
Masked so it can't cheat by looking ahead?
Exactly. Their pre-training task is almost always next token prediction, just predicting the very next word in a sequence. Because their entire training is about generating coherent continuations, they are masters of natural language generation, NLG, writing text, chatbots, summarization, though sometimes abstractively.
Makes sense. Trained to predict next word, good at generating next words. And the third family.
The third keeps the full encoder-decoder structure, like the original transformer paper, but scaled up. Models like T5 or BART fall here. They leverage both stacks. Their pre-training often involves denoising autoencoder objectives. For example, you might feed the encoder a corrupted version of a text passage with spans of text masked out, and train the decoder to reconstruct the original, clean text.
Sort of like repairing text.
Kind of, yeah. This makes them very flexible. They can handle a wide variety of C2-sec tasks naturally, often framed in a text-to-text format, where the task itself is specified in the input text. Think translation, summarization, even classification treated as generating a label word.
Okay, so 3 flavors. BERT style for deep understanding, GPT style for generation, and T5 BART style for versatile sequence-to-sequence tasks.
That's a pretty good summary of the landscape.
Hmm?
So if you trace that whole arc, we went from models with very limited fixed memory to models with sequential memory, RNNs, that unfortunately forgot things easily due to vanishing gradients. Then we got the LSTM GRU gates acting like careful memory managers. Then the sec-to-sec bottleneck forced the invention of attention, allowing dynamic querying of the input. And finally, the transformer just went all in on attention, ditching recurrence entirely for massive parallelism.
It's fascinating how each step was really driven by overcoming a specific limitation of the previous one. And the big takeaway seems to be that the fundamental nature of the model, is it better at analyzing existing text like BERT or generating new text like GPT that's largely baked in by how it was initially pre-trained? Fill in the blanks versus predict the next word.
Architecture, or maybe pre-training objective, really is destiny in this case.
Okay, so final thought for our listeners to chew on. You mentioned multi-head attention lets the model track different things in parallel syntax semantics.
Right, different heads might specialize.
So imagine one head learns something really structural, like subject-verb agreement across a long distance. Another learns something more nuanced, like tracking emotional tone. What kind of really surprising, almost human-like skill might pop out if, just by chance during pre-training, one attention head got really, really good at just tracking negation understanding when a concept is explicitly not true, even when the negation is complex or far away from the concept itself in a very long, convoluted sentence.
Hmm, that's interesting. Tracking negation robustly over long distances.
Yeah.
That could lead to some very subtle reasoning capabilities, or maybe just make it much less likely to make certain kinds of logical errors. Definitely something to think about.
Something to mull over. Thanks for that amazing tour through AI history.
My pleasure. It's quite a story.